Parisa Rashidi, who is an associate professor at the University of Florida. Welcome to the Data Exchange podcast.
Thank you, Ben. My pleasure to be here and to have a chance to talk about this topic.
So your background and training is in machine learning, but even from graduate school, you've had a strong interest in healthcare and medical and biotech related applications. So can you describe how you ended up mainly working in these areas?
Yeah, very good questions. Yeah. So my background and my training is all in computer science, computer engineering, and more specifically in machine learning. Nowadays, you see me working a lot in the medical domain, and it has not been a straightforward path in a sense that when I started working in this area, and especially in a biomedical engineering department, which is these days my primary appointment, there were not many people working on this type of problems. But I guess we are seeing more and more people working at the interface and intersection of machine learning and healthcare. And I think that's an area that is growing really fast. So starting with my graduate studies, I was working again in an interdisciplinary team, and we were trying to build a sort of smart home that was using sensors to track the activities of older adults who might be suffering from dementia, to check their physical and cognitive function over time and to track it. And then once I became a faculty, I kind of continued along the same line. I expanded my work a little bit. These days, I'm not working so much in community settings, and most of my work is in acute care settings, critical care, or perioperative setting. But that's the short version of how my career path got me here.
So one of the reasons I have you on is you are part of a team that wrote this interesting survey paper on the applications of deep learning to electronic health records. So let's do a little bit of a deep dive into this area. So first of all, Parisa, for the people who are not familiar with electronic health records, which we'll call EHR now for the sake of this conversation. So what makes them challenging to work with, and what are they exactly?
So electronic health record systems, as the name implies, those are the systems that we use for storing information related to patients and their encounters with the providers. And that can mean different types of information. For example, demographics information such as age, diagnosis information, the procedures that have been done on patients, laboratory tests and results, the medications that have been prescribed. And those are the type of data that are structured data, which means that you can store it nicely in a table with rows and columns, just a single value, and that's easier also to be processed. You also have unstructured data in EHR systems, which is typically in form of clinical notes, such as HNP notes, progress notes, discharge notes, as well as some of the medical imaging data that you get, for example, from MRI, CT scans, these type of image modalities. So really, you have structured data and unstructured data in the same place. And the structured data is interesting in EHR system in a sense that you have even more structure than most of the other types of data. Because, for example, for something like diagnosis, you need to have codes in place. So we have certain vocabulary systems that we use for example, diagnosis. We call it, the most widely used one is ICD that we use, ICD-10 at this point. ICD-11 is going to be available also soon. And it's like 68,000 different codes that we use in order to document the diagnosis. What is the patient condition? You have the same thing, for example, for the type of procedures that are being performed on patients, for medication. So in a sense, it is very structured. At the same time, you have unstructured data. And that's actually one of the challenges, because you have heterogeneous multimodal data in just one place. And the EHR systems, these days, they are very widely used in the US. That kind of got started mostly around 2009 when we had the HITECH Act during Obama administration. That kind of provided like $30 billion incentive to hospitals to start using that. And right now, many places use that. And that's a very good source of information for us as researchers.
So a few quick questions. So first, 68,000 codes, man. The classifier.
Yes.
I'm just imagining the classifier. And then
And that's
second,
just for ICD. That's just for ICD. You have
right,
also all the other types of codes.
right. And then secondly, even though it's structured, there's a temporal dimension, right? Because as anyone who goes into a doctor's office knows, the first thing they do is take your temperature, blood pressure. So all of that is probably entered into and updated into the electronic health record. Third, there's the entire regulatory HIPAA aspect that makes it sensitive to work with this data. So you have to really be careful when you touch these systems. So so obviously the paper is about deep learning, but what was happening before deep learning?
Wow, we could go back to a long time ago. Like if you go back to 70s, we had the expert systems like Mycin, for example, that was using basically
For
production.
they were using it for the same records, electronic health records.
Well, it wasn't exactly electronic health records at back then, but you are working still with medical data in a sense. So it's the same type of data, whether you are recording that in EHR systems in the form that we see today or not. That's a different story. But the type of models that were used with medical data, you have expert system, you had probabilistic systems such as Internist, for example. But those systems were
support vector machines.
Support vector, you around 2000 you have support vector machines being used a lot more, and around 90s you had also neural networks that were being used, but mostly on small data sets. But the support vector machines, really in 2000s, those became very popular, and especially in neuroimaging community, they have used that in so many applications. And then you also have models such as, for example, decision trees, and more recently gradient boosting machines such as XGBoost that can work really well with structured small data sets. Sometimes they can work better than neural networks.
So if I take away the notes, the physician's notes, and I just look at the structured side of the house, can I get by with non-deep learning these days?
Well, if you just
are the non-deep learning things competitive with deep learning?
If you are only taking very simple information, such as, say demographic information and maybe some simple demographic plus diagnosis information, maybe you could do that. Still, in some cases, especially if you look at the number of diagnosis codes that we have, discrete codes that we have, that's a lot. And you could use something like one-hot encoding, but it might be better to use something like embedding techniques where you could kind of reduce the dimensionality of those discrete codes and then use that better for forming nonlinear relationships in your data. That could help better. But so, I mean, with small data sets that have just maybe 40 variables, sometimes it might be better just to use, something like XGBoost. We know that.
So for those of you, Parisa, who work in this application domain, was there kind of like an ImageNet moment where the deep learning models just blew everyone away and everyone dropped everything and let's go to deep learning?
I'm not sure if that's something that happened like overnight. And I'm not sure if we have seen that kind of like, ImageNet moment yet. Definitely, we have some data sets that are kind of similar that are used by many people. For example, in the critical care domain, we have the MIMIC data set from MIT. That is kind of like a benchmark, and many people, including our group, we use that as a benchmark. Although like we have our own data set here at University of Florida, which is quite big, we still use mimic in order to do the benchmarking against that. So you have these data sets, But I still think there is lots of space for growth here. And this is an area that compared to something like, general computer vision or, general NLP is still underexplored. And some of the reasons are not technical. Some of the reasons are just because, it's a challenging area, as you were mentioning in the beginning, that you're dealing with systems that need to be robust. You're dealing with life and death situation that really you need to create algorithms that are really accountable. And also, like you have other issues, like, you have imbalance in your data set, you have missing data, you have so many different challenges and issues that need to be addressed. And it would take many years, many groups to get together and address those issues.
And actually, I forgot, we're finishing up an AI in health survey. Actually, I'll send you a copy. We had over 300 respondents. But one of the things we found actually is in healthcare, many of the systems, the goal is to get these AI applications in the hands of clinicians and users. So as you were talking, I was reminded, well, there's also UX, transparency, right? So, and as you point out, robustness and safety and reliability are super important. So I imagine none of these systems are really pure AI. They're always human in the loop. They augment some human expert, right?
Yeah, you nailed it. So one of the things that I usually like to mention in my classes is that I show them the technical debt paper, and I show them all the different components that we need in the whole pipeline system, in the life cycle management of a system. And really, most of the time, we as researchers, because it's so exciting, we are just focusing on the machine learning piece, on the deep learning piece, say. But there are so many different other important pieces. Take, for example, user experience, the UI. If it's not usable, it doesn't matter if you have created a very accurate system. At the end of the day, the doctors or the nurses, whoever is going to be the end user, they're not going to use that because it's not very helpful, right? They cannot use that very easily. The same thing goes for other pieces of, the whole pipeline that we need to pay attention to, like, the experiment design, how you're collecting data. If you are not collecting data in a way that we can draw the endpoint conclusions, then it's not going to be very helpful. So there are many moving pieces here, and really we need to have that big picture in mind as just, opposed to just the machine learning piece, which is the exciting part, but the other parts are also very, very important.
By the way, there's a UX component for the patients as well, because as those of us who go to doctor's office probably notice, sometimes the doctor spends more time on the computer.
There you go. Exactly.
Talking to us. So yeah. I think actually this is why this domain is also an area where speech technologies has a lot of utility, right? Because they can yes. Maybe it's just transcribed, right? So rather than them typing in front of them.
Exactly. So yeah, I think that's very important. And some of those systems like the EHR systems, there is opportunity for making them better, especially UI extensions or other types of extensions. But it's difficult, unfortunately, to kind of integrate into those systems. Usually those are closed systems, and to kind of modify that. So that's another barrier that we are facing.
So we have all of the data in the EHR. It's a mix. It's could be multimodal. There might even be speech data in there. So what are some of the actual applications and use cases? So I'm looking at the paper. So the first thing you cover is information extraction, which is a classic problem in computer science. So describe the impact of deep learning for information extraction in electronic health records.
So in terms of the information extractions, really, especially in the recent years, deep learning has helped a lot. And I think there's also lots of room for growth again in this area, because if you look at clinical notes, and that's where the information extraction usually comes into play, we can use all of the recent progress that we had in NLP. For example, the pre-trained model, in the past we had also the word embeddings, and now we are using the pre-trained models. And those can, yes, transformers, BERT, all, those different flavors of BERT that are coming. So we can use those in a couple of different applications. For example, we might need to extract temporal events from those clinical notes. When a certain condition, when the patient had a heart attack, was it October 16? Was it like 10 hours ago? When was it? So you're looking for this type of information. You're looking at relation extraction, which is basically the relation between two different entities, like a treatment and a medication. And sometimes you also want to extract more information regarding the context, and that can be a little bit challenging when you're dealing with clinical data because you have so many abbreviations. Like there are probably about 200,000 abbreviations in clinical text, and many cases those might be referring to more than one entity. For example, take MI. It could refer to myocardial infarction, heart attack, or mitral insufficiency, which is a failure of heart valve. And it's just the same abbreviation. And it makes it very difficult, even in the context, because again, we are talking about cardiovascular context to kind of differentiate between those. So there are lots of application for those. And again, clinical notes are challenging because you have domain specific knowledge. It can be telegraphic, incomplete sentences, you might have misspelling, all these sorts of problems that you might not see, for example, in a scientific paper.
So one of the things that I'm learning as I talk to people who work in healthcare is, in many ways, healthcare, as you point out, many of the models and the use cases are similar to classic NLP, for example. They just are always harder, right? Because
that's a good way to put it.
one particular reason is there's so many subspecialties. So the way people talk in radiology might be different in another field, which brings me to a very practical question, which is, I take a model, let's say some form of BERT or some variant. Let's say it's tuned for some medical area, radiology or something else. Obviously, I cannot point that to another area of healthcare, right? So I have to retune it a little bit. So how hard is it to tune? How much data do you need in order to take something you read from a paper and apply it to one of these healthcare situations?
That's a good question. I'm not sure I have a very good answer for that because it would depend on the domain. For example, if you're talking about biomedical images, if you're taking ultrasound images from another body part, and then you're taking ultrasound images that was taken in another institution, and then you try to do transfer learning between them, just doing some tuning and tweaking, then it might not take as much data. But if you are, say, starting from something that is really different and then tune that, then it might require more data. I would say typically you're looking between about 1,000 or maybe 5,000 data points in terms of units in order to tune a model well enough. But again, that depends on the domain, and sometimes it might be more difficult, and depending on how imbalanced is your data or non-missing data, that could be different. But that's a very good point, because you cannot just take, a model that was developed here at UF and deploy it, for example, somewhere in India or even somewhere in the US that has very different guidelines for treatment. That's not just the right way to do that.
So in the course of your work, do you find yourself building a lot of data annotation and data labeling tools?
Yes, a lot. Actually, I would describe it as probably like 20 or maximum 30% of our work is spent on, building the actual machine learning pieces. Most of it is cleaning data, designing the experiments, especially if you are collecting our own data. making conclusions about data, just sitting down. For example, my longtime collaborator, Dr. Ajra, she's a nephrologist. We sit down together and we look at the results for a long time. We try to make sense of it and then go back and try to run a different experiment. So really, again, we are going back to that pipeline. That pipeline is a lot more than just the machine learning piece that goes into that. And I think it's very important also for everyone, especially students who are new to this area, to realize that it's just more than the machine learning, and collecting data that should be as important. Assigning metadata to your data, it should be as important, and making sure that at some point, if you can, sharing data in a way that is accessible, that is fair, that's also very important, how to do that.
So other use cases that you folks cite in the paper are representing discrete medical codes and predicting outcomes, both static and temporal. So one high level question is, not only is it harder in healthcare, but obviously you have to be more careful, right? So do you folks have very specific processes and standards for how do you QA, how do you test, how do you make sure a model is robust before you actually say, okay, this is ready for physicians to use? So what is the process to go from something that's a prototype to production in this area?
Usually it takes many, many years. So it's very important, especially for models that are developed in this area, to go through many, many different iterations of testing and many different types of testing. Initially, for example, the deep SOFA paper, that is one of our works that we have done, we did the testing in an internal manner, which was basically we used a large data set that we had collected at University of Florida. We trained on that, and then we tested on a separate subset of that. Then we do external validation. If you have access to another data set, for example, from another institution, then you do external validation to kind of see how well your results can generalize, say, in Boston versus Florida. Does it work? And in our experiments, most of the time, we see a decrease in performance, which is what you actually expect. After that is the most important thing that actually these days we are missing from literature. You just see it in a couple of examples in literature, which is prospective validation. So once you have done careful internal validation, external validation, multi-center validation, then you have to move on to prospective validation. And usually the first phase of that would be in a silent mode. So really you're not providing any recommendation to the physicians, nothing. You're just observing data as it is coming in real time, and you are making prediction, and then later you compare to the actual outcome. And after that would be the actual prospective validation, that you might even use that in a limited manner to make recommendation to the physicians. But the prospective validation, it's difficult in many senses. For example, in terms of the administrative work, regulatory issues, and also many people don't kind of advance to that stage. Most of the papers that you see in the literature, they do just internal validation. And sometimes they might do external validation. Rarely they might do multi-center validation. And very, very rarely they might do prospective validation. But that's the process that you should go through, really.
So many of us wear smartwatches. Like I have an iWatch, right? So there's all sorts of healthcare apps in here. But there's also medical devices that you use in doctors' offices that are increasingly getting augmented with machine learning. They go through a formal approval process. So what about the things that you've been describing, the things that are in an electronic healthcare record? So you talked about the stages of validation. Is there a formal regulatory framework for deploying the types of models that we've been discussing?
Yes. So FDA is similar to the same procedure that we have for medical devices. You have a similar procedure that we have for AI algorithms. And there are a number of dozens of AI algorithms that have been approved through that process. And they have to satisfy a number of requirements, for example, in terms of accuracy and their performance, and they go through tests. And also I believe also it's important to be able to explain how the method is working in terms of transparency and auditing. So FDA is aware of that, and there are procedures in place. But usually that would come also after the prospective validation. Once you're happy with your tool, then you're like, okay, we are ready. So we should take it to the prospective, to the regulatory aspect, and we should do the approval for that. So that's the ultimate goal, that you're doing translation of your research, hopefully at some stage. It's not just staying at the research, academic interest sort of thing.
So as you describe prospective validation, it seems to make sense. It seems like it's something everyone should do. So why aren't people doing it as a matter of routine? Is it just because it's an extra layer of scrutiny, so to speak, or is it because academics are under the gun to publish papers?
Both. I think you're pointing to two very good reasons why we are not doing that. And I think we are in a publish and perish type of situation where most researchers, they are publishing, and once you have published a model that is state of the art and you're showing that it is performing well, taking it to the next stage and again repeating the same experiment but in a different manner, really in some communities that might not have as much value as moving on to the next state-of-the-art machine learning model. So the incentive that we have for publishing, I think that needs to be changed. That infrastructure is important. The operations, the underlying operations are important. Prospective validation are important. And prospective validation is important in the clinical community. But for people who are working at the intersection, if they are doing that in the machine learning communities, sometimes it might not be valued as much as developing a new model. But hopefully we will see that more and more often as we see more people valuing the real world applications.
Speaking of which, the work around deep learning in electronic health records. So, how much of it is out in the real world already?
Well, there are a couple of applications and there are a couple of algorithms that have been approved by FDA. And of course, researchers in academic centers, they are using these models, they are developing those models, but really deploying that in the sense of being really integrated in an EHR system like Epic, we don't see it very often because of the reasons that I mentioned, that it's difficult to integrate with EHR system because of all the administrative issues, and it's difficult, privacy, security. You have to address all of these issues which might not be part of your core research. So many times people don't go through that, and then they just stop at the point where they have the model, it's working, it's performing well, it is accurate, let's move on to the next project.
So there's Parisa, isn't there an EHR system for the VA, which is also pretty big? So it might be easier to deploy if you work through that kind of VA system.
I haven't worked with them, but typically still you have the same type of issues. For example, privacy and security. You still have that kind of issues, and it's understandable. You have to make sure really that the models that you are using, those are also transparent. Really, lots of the issues are kind of universal, and it really doesn't matter whether you're working with Epic or VA or some other EHR system. The integration might be a little bit easier in some of the system versus the other ones, but the core issues, which is privacy, security, transparency, the ability to audit a model, those don't change when you go from one system to the other.
So, which brings me to responsible AI, which I think healthcare obviously is ground zero for making sure that all these areas around responsible AI, transparency, privacy and security, safety and reliability, robustness, fairness are checked off before you actually move forward. So let's talk about some of these areas briefly. So I guess in the area of transparency, it's almost like as someone who's organized many conferences, I would say that whenever there's a talk about explainability from healthcare or finance, it's a popular talk because I think the audience recognize that these are the people that really have to make sure that their models are explainable and transparent. So, is part of the answer here, Parisa, making sure that as you build a model, you are building it in conjunction with some of the users and domain experts so that they feel like they have some input into the model building process.
Definitely. I think you're making a very good point that we need to involve all the stakeholders when you're building those models and those systems. And that also applies to interpretability, explainability, transparency. To understand, well, what do we mean when we say a model should be explainable? What should the output look like? What do they
there's no
expect?
clear
Right?
metric, right? It is a, I guess the way it's been explained to me, it's more along the lines of social science, right? So you have to have like a
Definitely.
panel of people to, yeah.
Yeah, so you need to have like, focus group, usability studies, and then understand the issue and then provide a solution. Sometimes we as engineers, I'm guilty of that too. We love to provide a solution and then go back the other way. But really, it should be started at the problem, really understanding the problem. For example, recently we had another survey paper on interpretability, explainability on time series data. And that's an interesting area because when you're looking at time series data, like physiological signals that you capture in the ICU, what do you mean when you want to have more interpretability? Like, what would you show? Would you show complete patterns? Would you show like summarized information? And really, I think that we are missing that step that we go back to the doctors, we do lots of usability studies, we do lots of interviews, semi-structured interviews, focus group, ask them, really, what do you want to see? Or really, do you want this information, or is it just going to be another information overload system that we are giving to you? I don't know. We
So
have to find out.
what did they say for time series? Do they want to see spikes? Do they want to see anomalies, or what did they want?
I don't know. We haven't done that kind of experiment. This is something on my to-do list, and I think it's going to be very interesting. But I think that's going to be important to see what do they want, really.
So
There have been some recent works, but really there isn't much work in that area.
has this ever worked in healthcare as far as you know, which is basically I build a model, it's a black box, and then I go to the specialist and say, hey, this works. Just try it for a while. It works, trust me.
Yeah.
Will this approach ever work?
Well, you might get some feedback based on that, right? It's almost like, if you're working in a startup, you're building a minimum viable product and you take it to the stakeholder, you get some feedback based on that, and then you try the next iteration. But maybe if we start from the very beginning to see what's the problem, what do they want, that could also help a lot. And really, I think that that's where the future of AI and machine learning would be in the future, that it's going to become a lot more interdisciplinary in a way that it's not just going to be about quantitative sciences, it's also going to be about qualitative sciences, that we need to work, for example, with social scientists, with other disciplines in computer science, such as HCI, really to kind of make sense of data. It's not just about accuracy and a couple of metrics. It's more than that.
And sometimes, actually, honestly, it's not just about machine learning models in some ways, right? Because especially in healthcare, there's so much domain knowledge and expertise. We need better ways of capturing that knowledge. and using that to help the model, especially in the beginning when the model doesn't have a lot of data or proven experience, right? So
Exactly.
and then over time maybe start out with more domain knowledge, and then over time more of the model takes over, right?
Exactly. Yeah, definitely.
Um, so another area of responsible AI is privacy and security, and as you know, there's all sorts of exciting research in privacy preserving ML, differential privacy, homomorphic encryption, federated learning. Uh, are you hearing any of these things popping up in healthcare?
A little bit. So I think there is potential for all of this, especially something like federated learning and some of the privacy preserving methods, especially for data sharing and model sharing. Right now, as I mentioned before, we have a couple of data sets that we use. Everybody uses them, but really, what if I could use data from most of the major academic institutions in the US? What if we could get that data in real time? I know that sounds like, something that would be
All
a nightmare in terms of privacy and security, but what if we could do that in a very privacy preserving and secure manner such that the models can be trained much, much better? I don't know. We don't have anything like that yet.
Yeah, and then this is where maybe techniques like differential privacy or federated learning.
Exactly. Federated learning, for example, can be very helpful here for this type of situations. And that could help for sharing the data, for sharing the models in a privacy preserving manner.
So what about so when it comes to privacy, the canonical example in healthcare that people always cite is genomic data,
Mhm.
and increasingly that's going to be more common, right?
Mhm.
So in many ways, the stakes are getting higher in terms of privacy and security, right?
Yes.
Which means that either these either regulators have to do something and kind of and set the tone early, or consumers need to really pay attention to what they're doing when they're spitting into a test tube and sell it and sending it uh, to some genomics company, right? Because basically,
Mhm.
my understanding is a lot of these genomics companies end up selling their data.
Right. So
Uh,
this is a very complex discourse that we need to have. And I personally think that we should have a stance that is evolving over time. And it should be a trade off because we know that there will be lots of applications for sharing data and having genomic data, and at the same time privacy is really important. If you have very strict regulatory system in place, then it might kind of obstruct innovation, right? That's the problem. And if you have very lax regulations, then privacy, we might not have that. So really it should be a trade-off and it should be evolving over time. But you're absolutely right. It's not just genetic data. For example, last year, I believe there was a very interesting paper that showed that just based on MRI data, you could actually re-identify a person if you also have enough access to like one of those public data sets that have profile pictures just based on MRI, because this 3D, the three-dimensional skull, structure, it kind of matches the same profile picture. Just think about that. So it's not just genetic data, and over time, our methods are getting more and more sophisticated. So that's why I mean, it needs to be evolved over time, and we need to have a trade-off in this area.
So, in closing, so obviously, machine learning models get better and better over time. Uh, data collection improves, and there's more and more sensors like our watches and things like this. So, will there come a time when, and obviously, I think the answer here is no, where we can automate everything. We don't need doctors.
I don't think that will ever come, actually. We will always need doctors. It will be what we should call as conditional automation, that you still have doctors in the loop, but many of the low-level decisions, really, at some point, those can be automated, but you still have humans in the loop for the more critical decisions that need to be made.
And I imagine healthcare is kind of like self-driving cars, in the sense that it might be easy to roll out a system that can do simple things, but it's these dang edge cases, that you can never go fully autonomous, because it's just, life is complex. The human body is complex.
Exactly. And you know what? We train the doctors to be really good at detecting those edge cases. But our systems, they usually, the way that they are reporting the performance, even when we are looking at imbalance, type of performance metrics, still they kind of miss the point of how they should be trained. Doctors, when they are being trained, they really pay attention to those edge cases, rare conditions. We don't have the same type of training for machine learning models, I don't think yet.
By the way, in closing, one of the things that I really liked what you said about, and this is something that everyone says, by the way, but I think the sometimes the practitioners forget, is that at the end of the day, the modeling part, by the time we get to building models for doing somersaults, we're so happy. It's data collection, data annotation, data pipelines, data security. That's where the real work is.
Exactly. And those are very important in the healthcare domain. And we really need to pay attention to the entire pipeline. Those life cycle steps, those are very important. And it's also important to have continuous integration, continuous delivery, as we have with, ML ops, because if you don't have that, then your model might be working today, but 2 years from now, really the guidelines, the treatment guidelines, the policies, those change. So your underlying population, the case mix index, the treatment guideline, all of that has changed, but your models, if they are still the same, then how they are going to work? You need to continuously monitor the performance over time. So that's one of the other things that when we are looking at the life cycle, we have to kind of keep in mind, and we might need to, again, annotate data. And that's one of the areas that I think that something like, for example, active learning might be really helpful. We are not using that a lot to its full potential, but I feel like that should be quite important in the healthcare domain for selective annotation of data points, not just, oh, I have this batch of data, let's annotate that.
So one last question, I'll put you on the spot. So you just mentioned it's important to consider all these other things, ML ops, CI, CD, and so is this something that you find yourself doing as you train the next generation of data scientists, or are your classes still model heavy?
No, I try to actually include, recently especially, I have been trying to include more information about these topics. And this is a very rapidly changing field. And I know that just like many of the other people in this field, it's kind of hard, difficult to catch up with all the new knowledge that is appearing every day. But no, this is very important. And actually, recently, we tried to kind of build a new syllabus for a course that is including all of these different topics, the full stack AI, or, including ML ops. That's very important. And in academic settings, sometimes we are only teaching the machine learning part, but really all of this is very important, the way that we can develop reproducible models, containers. Those are practical matters, but really when you're deploying a model, how do you serve it? If you have a complex environment, how do you manage that? Those are very important. I know that those are also important for industry partners. So the next generation, they need to know about all of these topics. And we in academia, we need to teach them all of these topics.
And with that, thank you, Parisa.
Thanks for having me.